At the end of the previous lecture, I noted that one of the reasons behind Aristotle's great achievement in producing a system of great longevity and authority was that, on the one hand, he produced a system of natural philosophy, as well as, on the other, a method for continuing his work. In this lecture, we're going to turn to Aristotle's most immediate successors first, and see how they responded to his legacy. And then we're going to look at the larger Greek world, the Hellenistic world, the world that was created by the astonishing conquests of Aristotle's student, the great Alexander. In 335 BC, after an absence of 12 years from Athens, Aristotle returned to that city and founded a school which he called the Lyceum. Now, he had a precedent for this. Plato had founded the Academy at Athens previously. Aristotle had been a student with the Academy for 20 years. Instead, Aristotle founds his own school. And the Lyceum carried on some of Aristotle's natural philosophical projects. Well, not so long after, in 323 BC, Aristotle felt constrained to flee from Athens for a second time. This was because Alexander the Great had just died, and Aristotle was connected with Alexander the Great. He was his teacher. Aristotle had connections to Macedonia, and there was a vigorous anti-Macedonian sentiment that broke out in Athens. And so Aristotle left the city, saying that he would retire from Athens to prevent the Athenians committing a second crime against philosophy, the first having been the trial and execution of Socrates. Well, when he left behind his friend Theophrastus, who was a bit younger than he, as head of the Lyceum. Aristotle didn't live very long after he fled from Athens to Chalcis. He only lived a few more months. And so upon his death in 322 BC, Theophrastus assumed the permanent leadership of the Lyceum. And Theophrastus led the Lyceum for 36 years. What did Theophrastus do? Well, part of Theophrastus's most important work functions on extending Aristotle's studies of the natural world, particularly in two areas, in plants, what we would call botany today, and in mineralogy. Theophrastus wrote several authoritative texts on plants, in which he mentions over 500 different varieties of plants. The method that he uses is a great deal like Aristotle's. As Aristotle looked at the parts of animals and classified animals into different categories to produce what he called a history of animals, so likewise his successor Theophrastus wrote an exhaustive work on plants, looking at their parts, classifying them, and putting them in order, looking at how they function in the natural world. His work on minerals takes much the same tack, and both of Theophrastus's works, even though he wrote many, many more works than what we have now, we only have generally his works on plants and minerals, they were authoritative texts down until the 17th century on those two subjects. What's perhaps slightly more interesting is not how Theophrastus followed Aristotle, but how he disagreed with him. Because he disagreed with Aristotle on several issues. First, the elemental status of fire. He said that fire was not like the other three elements, earth, air, and water, and shouldn't even be classed as an element. He also disagreed with Aristotle on a really crucial point, the universality of final causes. We saw previously that Aristotle's interest in the final cause is a centerpiece of his natural philosophy. But Theophrastus instead says there are things in nature that have no purpose. His example are nipples on men. There is no reason for that. There is no final cause. The other thing that Theophrastus did, which was important in terms of practical matters, was that he bought land and buildings for the Lyceum. He had to get a dispensation to do this because only Athenians could actually own land, and Theophrastus was from the island of Lesbos. But he did, in fact, get dispensation. He bought land, he bequeathed it to the Lyceum for their perpetual use in common, which ensured the survival of the school. In due course, of course, after 36 years, Theophrastus died in 286 BC. The third leader, then, of the Lyceum, who took over from Theophrastus, was one Strato of Lampsacus. He headed the Lyceum for 18 years. Now, very unfortunately, none of Strato's many writings survive to us. Nothing that he wrote. The only thing we have are some snippets, some extracts copied down by Hero of Alexandria, which we hope Hero was a good transcriber, and so we have something of Strato. It's particularly sad for this course that we don't have more of Strato because he had the nickname Ho Physicos, which we might call the naturalist or the physicist. So clearly his primary interest was actually in natural philosophy. But he too disagreed with Aristotle on some fundamental points. One case, he discovered that falling bodies, remember a heavy object has a natural tendency to fall to the earth, he found that not only did they move toward the earth, they accelerated. They moved faster the longer they fell. That's Strato's observation. Perhaps more interestingly, he illustrated this by some simple experiments. One of them was to take rocks and drop them from different heights into soft earth and look at the size of the craters they left. But another one, which I think is just incredibly elegant, and you can watch this yourself next time there's a rainstorm, if you live in a house or an apartment with eaves on it. He said, if we drop a stream of water from the edge of a roof, right near where it's pouring off the roof, there's a continuous stream of water that's solid, like a solid pillar of water. But that only lasts for a few inches. Then the stream breaks into droplets. Now you've probably seen that. Well, Strato asked why. Well, why? Well, the water accelerates, and so the water lower down in the stream is moving faster than the water up above, so you can't possibly have a continuous stream of water from the roof line to the ground. The acceleration forces it to break into drops. The other thing that Strato commented on is the existence of the vacuum. Now, Aristotle would have nothing to do with the idea of a vacuum. Void space was inconceivable for Aristotle, and he posited lots of arguments against the possibility of there being a vacuum. Strato, on the other hand, seems to have believed that a vacuum could exist. And again, he designs a simple experiment to try this out. This is recorded in Hero of Alexandria. You take a sphere made out of beaten bronze or brass and fix a little tube on it. So it's like a balloon, essentially. They didn't have, they couldn't blow glass that way very easily, so instead they used brass. So it's sort of a brass balloon with a nozzle on it. And he says if you blow through the nozzle, you can actually force a bit of air into it. You put your finger over it, put it next to your ear, take your finger off, and you can hear the air rush out again. Well, says Strato, if the sphere was entirely full of air before, where does the new air go? How does it fit? There must be void spaces even when the sphere seems to be full of air because you can compress more air into it. If it were totally full, there'd be no more room. He also says you can inhale from the sphere and pull some of the air out. Again, put your finger over it, listen to it, and you can hear the air rush back in. So clearly, air can be dilated. Well, if there wasn't a vacuum before, there must be a vacuum then, because if the sphere was full, you've pulled something out, you must have left empty space. So there must be a vacuum. We have no proof for the following statement, but this kind of argumentation in favor of the void may in fact imply that Strato, of all things, was an atomist. Again, we have no clear evidence of this, but if that's true, then he's really diverging substantially from the ideas of his master, Aristotle. Now, I think it's significant that the two immediate successors to Aristotle as head of his school freely disagreed with him, and not on minor points either. This freedom to criticize is crucial to the development of Greek thought, and I think you'll agree that it's crucial to the proper functioning of modern science. We cannot have a single authority that tells us the way things in the world are. We need constantly to break down our former ideas and develop new ideas and new questions. And this is what's happening right here at the Lyceum. Well, the Lyceum continued to function for over 2.5 centuries, until it closed in the middle of the 1st century. Well, we've concentrated on Athens for the most part of 4 lectures now. We need to look at the larger world, because the ascendancy of Athens as a cultural center came to an end towards the end of Aristotle's life, largely through the actions of his one-time student, Alexander the Great. Alexander, who was born in 356 BC, died in 323 BC, created a vast empire. His conquests stretched out of his native Macedonia, throughout all of Greece, Asia Minor, the Levant, Egypt, out through Mesopotamia, Persia, through what's now Afghanistan, to India. So created an enormous empire in which Greek thought, Greek language, Greek customs, Greek trade could be disseminated. This period that it initiated is referred to as the Hellenistic Age. And we think of the Hellenistic Age as existing from the time of Alexander's conquests, around in the 320s BC, up until the time that the Hellenistic Empire, what was left of it, was absorbed into the Roman Empire, say the 1st century BC. Now, sometimes the Hellenistic period is seen as a time of decline in Greek natural philosophy, in Greek philosophy, in Greek culture. But this is really, I think, a matter of perspective. Certainly, in terms of natural philosophy, Hellenistic natural philosophers throughout the Hellenistic world were busy elaborating upon and following out the programs that had been initiated by the leaders of important schools of ancient thought: Plato, Pythagoras, Aristotle, Epicurus, and a few others. These various schools of thought were busy doing things, and what I want to show you for the second half of this lecture is some of the things that they were doing. Let me just posit that when we hear sometimes people talking about the Hellenistic Age as a period of decline, I think largely that's sort of a prejudice that comes down to us from the 19th century. This is my opinion. That looks, where in the 19th century people look nostalgically towards Athens as the pure Greek pinnacle of ancient civilization before it was contaminated by barbarian influences. That's certainly an opinion that Aristotle himself might have shared, but whether it's actually a useful historical way of thinking about the period is open to some question. Where I want to take us now is across the eastern Mediterranean, south from Athens to Alexandria in Egypt. The city of Alexandria was founded in 332 BC by Alexander the Great. Let me pause for a second. I have to be very specific. I'm talking about the Alexandria in Egypt because Alexander certainly liked his own name. He founded well over a dozen cities by the name of Alexandria. The one in Egypt is one of the few that still exists, but there are many others, most of them renamed in the time after. Egyptian Alexandria became a major center for Hellenistic thought and culture. And the more I read about Alexandria, the more I realize that that's a place I would really like to visit. One of the places that was founded there around the year 300 BC was the museum and the attached library. I think everybody's heard of the Library of Alexandria. At its height, it had probably 500,000 volumes, certainly the largest library of antiquity, probably the largest library that existed for the next probably 800, 900 years until the great libraries of Baghdad. It was supported by royal and other patronage. Now, this is an important point. We haven't seen that before. This is the rulers giving some kind of financial support to scholarship. That's unusual, but it becomes more and more important as time goes on. And I have to admit that the royal support of the museum and the library was sporadic. Strato spent some time in Alexandria. He may in fact have helped getting things started there, or certainly perhaps did some study as well. I should also say that the museum, don't get it confused because we use the word museum now to talk about an art museum or a natural history museum or an air and space museum. Museum means a temple to the muses, and so not only was it a place of learning, it was actually a place of religious function. Fine, well, who was in Alexandria that we would know? Well, one that comes to mind is Euclid the geometer. He was connected with the city for a while in the 3rd century BC. Euclid is famous for his axiomatic and deductive system of geometry. I won't say very much about Euclid because any of you who have taken 9th or 10th grade geometry have learned by Euclid's methods. The methods that we use in high schools today, generally, I hope, are still the methods, at least when I took it, they were still the methods of deductive and inductive proof, demonstrations, that was pioneered, really, by Euclid in the field of geometry. Another person of particular interest is Eratosthenes, Eratosthenes of Cyrene. He was born about 276 BC, died around 195 BC, and for a time was head of the Library of Alexandria. Among his most interesting accomplishments was a measurement of the size of the earth. He had heard that there was a place in Upper Egypt, that's the south part of Egypt, in the town of Syene, which is the current city of Aswan, where on a certain day of the year, a gnomon, remember a stick stuck into the ground perfectly vertical, a gnomon would cast no shadow. Well, at the same time, on the same day, in Alexandria, a gnomon would cast a shadow. So what he did was to set up his gnomon, measure the angle of the sun, how far off the angle of the sun was from directly overhead. He realized from simple geometry that that angle would be the same as the angle at the center of the earth between a line to an Alexandrian gnomon and a line to the Syene gnomon. Then all he had to do was measure the distance between Alexandria and Syene, and then divide 360 degrees, the whole circumference of the earth, by the angle subtended between those two places, multiply that by the distance between the two cities. When he did this, he got a value of 250,000 stadia. How good a measure was that? Well, unfortunately, we don't exactly know how long his stadia were. Generally, there are about 10 stadia in a modern mile, more or less. So, if that's the case, we can probably say with pretty good confidence that Eratosthenes' measure of the circumference of the earth was right within maybe 15%. It might have been as good as 2 or 3%, but certainly within 15, maybe 20% at the outside. Eratosthenes' measure was known for a long time. People remembered it. Elsewhere in the Hellenistic world, further developments occurred in several areas of natural philosophy. In astronomy, the one person I'd like to mention is Hipparchus of the 2nd century BC. Hipparchus did a lot of very interesting things. We're going to talk about him more in the next lecture. One of the things was to compile an extensive catalog of stars, where they were in the heavens, their brightnesses, and that sort of thing. I might add, sort of a charming point, that modern astronomers still use a catalog which is called the Hipparchus Catalog of Stars. It's not the one that was put together by Hipparchus the man, it was the one that was put together by Hipparchus, the orbiting satellite, in the 1990s. But that's a nice tribute to the work of this ancient Greek astronomer. He also measured the distance between the moon and the earth. He could do this because he knew that a particular eclipse was total at the Hellespont, while at Alexandria 1/5 of the sun's disk remained exposed. Therefore, Hipparchus could draw a triangle with its base stretching from Alexandria to the Hellespont, and its opposite point placed on the edge of the moon. Now, the very small angle at that far point on the moon must be equal to the angle subtended by the visible portion of the sun, that is 1/5 of its disk, or about 6 seconds of arc. Thus, Hipparchus could estimate the height of the triangle, that is the distance to the moon, as being between 71 and 83 Earth radii. He later re-estimated this to be between 62 and 72 Earth radii. The modern value is about 60 Earth radii, so not bad accomplishment. He also, if you want to be impressed by something he did, he determined the length of the lunar cycle. It's about 28.5 days. He determined the length of the lunar cycle, that is from new moon, to within 1 second of the currently accepted value. 1 second. He was able to do that because he had at his disposal the records of hundreds of years of lunar observations from the Babylonians. So he had a long enough period of time so that when he divided out the individual cycles, he got something that close. Last person I think I'm going to talk about is Archimedes. Archimedes was born in 287 BC, lived until 212 BC, unfortunately died a violent death, somewhat by accident, which I'll talk about. He studied at Alexandria for a time. Alexandria attracted scholars from all over the Greek world. Many decided to stay there and live, some went to study and then went back to their homes. Archimedes was one of the ones that went back to his homeland, which was Syracuse in Sicily, and there he produced advanced works on mathematics and mechanics. Some of the things he did. He tried to calculate the value of pi, and he came up with a value which was within 0.02% of our currently accepted value. He also wrote an interesting text called the Sand Reckoner, in which he tries to work with really, really large numbers. And this is not necessarily so easy to do given the Greek notational system. It would have been easier to do in cuneiform in the Babylonian system, but he did it in the Greek system. He attempted to calculate the number of grains of sand it would take to fill the universe. Quite a large number, that. What else? Well, Archimedes' work in general shows a further step towards the mathematization of natural phenomena. He wrote some fairly complex mathematical works on the spiral and on other things that are difficult to render in mathematical terms, and developed some quite complex methods of dealing with it. Tales of his cleverness already in Antiquity reached heroic proportions. He's another great figure of the early history of science and technology, like Thales became. This is particularly in regard to his technological wonders. He described several simple devices. For example, the screw, the Archimedean screw, which is a screw-shaped tube mounted on an axle. You can turn it and pump water out of, say, an irrigation ditch or out of the hold of a ship, uphill and out. It's still used in some places in the world to this day where there isn't more modern machinery used to lift water. He also studied the principle of the lever. He is renowned for saying, "Give me a place to stand and a lever long enough and I'll move the earth," to express the power inherent in using lever arms. He also devised a spherical contrivance, some kind of mechanism that represented the motions of the moon, the planets, and the sun. Now, unfortunately, this no longer survives. It survived long enough to be seen, described, and marveled at by the Roman orator Cicero. Fortunately, we don't actually know how it functioned. I should mention that a very interesting, a very dramatic thing occurred just a couple of years ago. In 1998, the world was thrilled to find that there came on the auction market a manuscript which to the naked eye looked essentially like a medieval Byzantine church manuscript, but underneath there were faint outlines of a previous text that had been written on the parchment. In fact, it turned out to be a 10th century copy originally of the works of Archimedes. And in that document is preserved the only Greek original of one of Archimedes' documents, along with several other books. This kind of manuscript is called a palimpsest, which literally means in the Greek wiped off again or rubbed again. It was a common practice because parchment was very expensive. If you had a book that you didn't read very often, which probably would have been Archimedes on advanced mathematical topics, you could scrape the ink off of it, in other words, rub the parchment again, because parchment is rubbed first before it's used. Rub it, cut it to a different size, and then write over it again. The original of this manuscript was made in the 10th century. By the 13th, I believe, century, it had become uninteresting to the owner. It was scraped off and used again to print a liturgical text for the Greek liturgy. The document is now at the Walters Art Gallery in Baltimore, undergoing conservation and study. And hopefully we will have some results from it in the near future, some further results from it. It was already transcribed in the early part of this century when it was first discovered, and then it disappeared for a period of time, but now it's been found again. I think the take-home message from this is to realize how tenuous our grip on the past really is. That we could have this text appear, disappear, be the only surviving copy. So many times already in these lectures I've said that the natural philosophers or Greek writers wrote so many texts and we have nothing left of them. Really, our hold on the past can be extremely tenuous, and that's an intimidating thought, I think. Archimedes' most famous principle, however, is the one that caused him to run naked through the streets of Syracuse, according to the story. The story goes that the king of Syracuse had a crown made for himself out of gold and was concerned that the goldsmith had cheated him and instead debased the alloy by mixing it with silver, or perhaps produced only a gilded crown rather than a solid gold one. So he asked Archimedes to find out whether the crown was solid gold, but without damaging it. He couldn't just sort of take a hacksaw and cut through it and look in the middle. Archimedes thought and thought over this, and again, according to this wonderful story, he was getting into his bath one day, and he realized that as he sat down into the bath water, the bath overflowed. And the amount of water that overflowed was equal to his own volume. The sudden realization of this made him realize that he could figure out the density of the crown. He could dip the crown and gold and silver into water to measure to see whether the crown actually had the same, what we would now call density or specific gravity, as pure gold, or whether it was less, closer to silver. So thrilled by this, he jumped out of the bath, ran down the streets of Syracuse, yelling, "Eureka! Eureka! I have discovered it." Well, wonderful stories about Greek antiquity. Another story, however, for which he achieved a great deal of fame, occurred when the Roman fleet, because now we've gotten to the beginning of the 3rd century BC, a new power is appearing on the horizon, that of Rome. The besieging Roman fleet reached the island of Sicily and began to besiege Syracuse. And the siege lasted for 3 years, from 215 to 212 BC. The story is that Archimedes set up bronze mirrors around the city walls and at the appropriate moment reflected the sunlight onto the Roman fleet and set it on fire in the harbor. Now, whether that's actually true or not is open to some question, but it's a good tale. We can see, however, what Archimedes really thought was important, because his last wish was to have inscribed on his gravestone a cylinder with a sphere inscribed within it, to memorialize what he thought was his greatest accomplishment, presumably, discovering and proving the proportion between the volume of a cylinder and the volume of a sphere inscribed within it. So we can see there that if, in fact, the stories about Archimedes' technology and technological advancement are true, where he put the relative emphasis, more on the impractical, we would say, knowledge of proportionalities of geometrical figures. This mathematical accomplishment of Archimedes is a good place to end this lecture. For in the next lecture, we're going to examine another part of Greek mathematics, where Greek mathematics was applied very successfully to create a system of astronomy that would endure for 1,500 years.